All right. So electric potential. With electric potential, we're going to do some analogy work, okay? So first of all, let's talk about what we're comparing. We're going to compare forces versus energy. And this is kind of a double comparison because we're going to compare forces versus energy, but we're also going to compare charges versus mass, or really charges versus gravity. So this is going to be like a 2x2 grid of comparison, but you'll see what I mean in just a minute. So first I want to hit on the gravity things because it's nice to have like some familiarity to lean back on. So with gravity, we talk about forces as being Fg equals that Cavendish constant G m1 m2 over r squared. And then continuing on maybe like across the horizontal, if we want to talk about how we've dealt with forces for electric charges, we had said that electrostatic force was K times Q1 times Q2 over R squared. And we might have talked about having absolute values for Q1 and Q2, but I'm just going to leave them off for now just to keep it nice and clean and simple looking. And so those are the comparisons that we've been able to make in the past. I want to introduce a new thing, and when it comes to, let's call it potential energy, potential energy in a gravitational situation would be Eg equals negative G m1 m2. And we talked about why the negative sign is there. I'll just leave that there. Any guesses as to what the structure for the equation is for the electric charge analog equation?
Negative Q, K Q1 Q2 over R squared?
Yeah, K. I'm going to leave the negative sign off. And the reason I'm going to leave the negative sign off is because we can actually have positive and negative Q values, while we can't have positive and negative M values. So for this one, I am going to leave the negative sign off. So that's like the only difference in terms of the structure here. And as far as like electric potential energy is concerned, I just want to do like a little aside, focusing on charges. Let's do a little subtitle here. Focusing on charges and work. So if we just think about charges and work and how those things would come together, I want to suggest that I have a charge that I'm going to call a point charge. So I'll call it just like Q point. All that really means is that there's this charge that's all focused at one spot. And we only really are considering point charges for this unit. We're not talking about like charge distributions spread out around a sphere or some other large shape. We're just going to talk about what I'm calling point charges, charges that are all concentrated at effectively one location. But if I had a point charge and I had another point charge, I'm going to call this one Q test. It's also a point charge, but just to differentiate between the two of them, if I have Q test and a point charge, and let's just say that they start off at a distance RA away from each other, and I'm using A to be like the initial distance between these two charges. So two charges that are a distance of RA away from each other. I need to make sure people in the room, can you see okay? Yeah. If you're too far away and you can't see, feel free to move though, okay? Because I am going to keep my marker the same thickness just so it all fits on the same page, okay? I think if you're watching it on a screen later on, I believe it's the right size. So, all right. So I've got these two charges that are distance RA apart, and let's just say that at some later point, I move them closer together so that they're at a distance RB apart. So this is location B. It's still Q point and Q test, but they've gotten closer together. Now, I want to make like sort of a reminder of what it was like when you played with magnets for the first time. And again, I'm conjuring up the idea of a third field. So we've talked about gravitational fields, we've talked about electric fields, and that's where we're going to focus today. But if you can remember what it was like to play with magnets when you were a kid, you know that when you push magnets together that are opposite poles, they repel off of each other, just like these positive charges are going to repel off of each other. And that means you must have exerted force on the charges, like to get them to do that. And if you exert force while you push something through a distance, then you must have done work. And we've kind of been here before. We've talked about how it takes work to change the the gravitational potential energy of an object, during rocket liftoff or whatever. But I want to propose that we could do work by changing the electric potential energy, or moving these two charges closer together. So I'll just make a little sentence statement here. Work is done when we bring two charges closer together or farther apart. And generally that's just true, because we've either pushed them closer together against the will of the charges. We've worked against their natural repulsion, or we're spreading them further apart, and that's sort of releasing some energy as they get further and further apart. But somehow work has been done, and we're just expanding our meaning of work, a change in energy. So moving on with this idea of work, I'm going to make a little jot over here. We're thinking about work. And as we think about work, we know that if it's a change in electric potential energy, then that would be electric potential energy. Well, I guess I've called it position A and B in that previous little example. So let's call it electric potential energy B minus electric potential energy A. And I'm using A's and B's for my initial and final here. And the reason I'm doing that rather than ones and twos is because it's likely that you'll have a charge 1 and a charge 2. And so I don't want to get confused between my 1 and 2 that mean charge 1 and charge 2 as opposed to my 1 and 2 which means initial and final. And I hope that that's clear. So if I expand this out though and I say, okay, electric potential energy for B would be K Q1 Q2 over RB minus, and then electric potential energy for position A would be K Q1 Q2 over RA. Yeah, sure, by all means. A lot of times when you see this kind of expression, say in like a textbook or something like that, you'll see the following thing. And just so that you're not sort of mystified by the mathematical magic that's happened, notice that there's a KQ1, Q2 in each of them. And people always come and say like, oh my goodness, how did it become like this? But I'm being like really clear about this. It became like this because they're common numerators. So we'll say 1 over RB minus 1 over RA, just so that that equation doesn't confuse you if you see it in a textbook. Yeah. Oh no, so for electric potential, oh my goodness.
No, I was going to say the squares up above.
Thank you. Somebody spoke up. I made a mistake. Those should not have been squared. Thank you for fixing that.
Oh, that makes sense.
It does make so much more sense. I'm so glad somebody said something.
I wrote it down without them. I'm wrong then.
You're right. Thank you. Not squaring the R's. Oh my gosh, that's so embarrassing. Wow. My mother wouldn't be proud. All right, so I want to stop there, okay, with the energy. And I want to switch my attention over to force. So I'm sort of bouncing back and forth between this idea of energy and force. If I go back over to force, I could say, well, electrostatically, force is equal to K times Q1, Q2 over R, this time R squared. And I know from the past that electric field is equal to Fe over, I could call it Q test. I'm going to call it Q2. The electric field that's the charge that's in the presence of an electric field. So maybe I'll just make a little note to myself. Sometimes we call it Q2. Sometimes we call it Q test. But it's that charge that finds itself being influenced by another charge or by an external electric field. Just on topic 4. That's what you're looking for, okay? And then if I take equation 1, let's just call it, and equation 2, and I sub equation 1 into equation 2, then I'll end up with kind of a cute equation that would be, let me get this right, epsilon is equal to K times Q1 times Q2 over R squared times Q2. And just to point out, that if this was equation 1 subbed into equation 2 producing this result, Q2s are going to cancel out, which means that epsilon is equal to KQ1 over R squared. So we've had that before. And I just wanted to make sure that it was sort of like coming up again with this idea of putting together our past knowledge to get forces and electric fields. And it may be useful in the homework. I think I'm going to pop over to the right-hand side of the page now and take a look at this idea of electric potential energy and do a little bit more, I don't know, let's call it derivation if you like, or just putting things together to make useful equations. So there's this new thing I want to try and do. If I take electric potential energy, that's that E, not the curly E, not the epsilon, but like capital E sub E, electric potential energy divided by Q test, I want to see what happens with that one. And in terms of like an equation that would expand out, that would be K times Q1 times Q test, Q test and Q2 I'm using interchangeably, right? Divided by R times Q test. And the Q tests are going to cancel out. And I get this kind of weird expression that's V equals electric potential energy over Q test, which is equal to KQ1 over R. And I just pulled that V out of nowhere. I want to explain myself now. That V is what we call electric potential. And when you were in grade 9 science, probably, you talked about how much energy per charge would have dropped across a light bulb, or how much energy per charge was given by a battery source. And that's really what we talk about when we're talking about voltage. We're talking about how much energy there is per charge that changes across a load or changes by increasing it across a source. It's still the same idea. So I just want to make sure that's really clear. We haven't changed what electric potential is. We're just kind of talking about it in a little bit more mathy detail than you probably did in grade 9, and that's fine. But this is electric potential, and I want to point out that this is not electric potential energy. That's E sub E. Electric potential is voltage, or electric is measured in volts, and that's not the same as electric potential, or is not the same as electric potential energy. Electric potential is this guy. Electric potential energy is this guy. And you can see by the equations that they're not the same thing, but let's just take a look at the units. Electric potential energy has units of joules. Electric potential, yeah, I've already said that it has units of volts, but you could break down volts. Look, joules per coulomb. Volts is equivalent to joules of energy per coulomb of charge that's present. It's not even the same units. And I've been trying to make these analogies between gravitational situations and electrical situations, and this is where it starts to break down a little bit. So if I really was desperate for an analogy, I could say, well, how is this going to hold up in a gravity situation? Well, in a gravity situation, I'd approach it like this. I'd say, hey, the gravitational potential energy, Eg, divided by not charge, like we did with the EE over Q, but divided by mass, some test mass, call it M2 if you like, would be G M1 M2 over R times M2, because that M2 is in the denominator. The M2s would cancel out, and you'd have something like negative G M1 over R, which is something that we've never looked at before. I mean, if I looked at the units of what this would be, this wouldn't be joules per coulomb, like with electric potential. It would be units of joules per kilogram. And I think to myself, well, why would that be useful? And I can't think of a useful purpose for this idea of what I would call gravitational potential. All I know is that value there would describe a point in space. That's what the R value is. A point in space above a planet, perhaps. So somewhere out here, there'd be a point above a planet that's a distance R away from the center of that planet. And at that point in space, there would be a certain amount of joules of potential energy for every kilogram of stuff that I put there. And I can't think of a reason to care about that. But that would be the gravitational analogy here. Okay, so if we're looking for something that's like tactile that we can think about because we're good at thinking about mass and stuff, then that's the best I can do, because there just isn't a better one. Because with electric potential, what we're saying here is if I take, and I think I'm going to draw a picture for this as well. Instead of my planet with a satellite kind of situation, let's think about like a proton. If I have a proton and I go out a certain distance away from that proton, I'll call it R1. If I go out a certain distance away, R1 from that proton, then anything that is that distance away, I'm going to try and draw a good circle here, but you can criticize it later if you want to. Anything that's a distance R1 away from that proton is going to have the same electric potential, according to that definition, KQ1 over R, right? Same electric potential. And anything that moves out to a distance, let's just call it R2. Anything that is at a distance of R2 away from that proton would have an electric potential associated not with R1 anymore, but with R2. And you could keep on going. You could keep on having like more and more and more rings, right? And as I look at this, I think like, oh, this reminds me a little bit, at least, of the way that we used to talk, like way back in grade 9 or grade 10, about having Bohr-Rutherford diagrams. We never really talked about it this way. Not really, right? But at least I can suspend my disbelief that, yeah, maybe we could have talked about it that way if Bohr-Rutherford diagrams had held up to the test of time. And as a theory, it kind of broke down. We started to adopt these ideas of sp and d orbitals and hybridized orbitals and things like that, just because we had to as we get up higher in the higher grades, right? But
well, we talked about exciting the electrons to release light with the Bohr-Rutherford diagram before we adopted the S&P.
Sure, you're right. So in grade 10, we did talk about jumping to higher and higher potentials. We never talked about them as potentials or as electric potential energies or anything like that, but we could have, right? We just said it was higher energies. And here we're kind of holding up that idea a little bit, and I don't want to be grade 9 or 10 about this. I want to be electrostatic about it. I don't want to try and say we're doing chemistry here, but I'm acknowledging that there's some overlap in where we've been here. And it's nice to build foundations or build our houses on old foundations, right? So we've got these different contours, and people will actually call these, they give it a name, equipotential. So jot that down, equipotential surfaces, or equipotential, I'll just say, or contours. Now, really, I kind of like the idea of equipotential surfaces better, because as I'm drawing this, because of the nature of a drawing on paper, I think of it as like a contour as I see it on paper. But the reality of this thing is that this isn't a two-dimensional drawing. Remember, as with all of these things with fields, we really are talking about a three-dimensional situation, where really each of those circles would be concentric spheres, wouldn't they? And I can't draw a sphere very well, which is why I have my trusty Titleist, just to remind you, right? Like this is like shells. These are concentric surfaces of equipotential. So that's just like something to keep in the back of your mind, that as we get further and further away, we're going to change the electric potential, but it doesn't have to be like in a two dimensions. It can be spherical. We can be moving outwards. So maybe I should just make sure that we have that down. Equipotential is what we call this concept. And then you'll find some people just call it volts. And that's like slang. Okay, but that's the units we use because it's named after volta. And if you take a look at these units, we've got volts, we've got joules, we've got coulombs. It's a whole bunch of dead people. And it kind of obscures the underlying units, but I don't think we're getting rid of the last names anytime soon. So if we ever do, hey, whatever, we can break it down into base units, and maybe some people are doing that, but I don't think it's happening anytime in the near future. So you had a question? Sorry? And
volts are acceptable for us to use?
Well, we have to use volts as the units, yeah. So I'm going to call it electric potential, but I'm going to name the units volts. And then some people throw in, they'll talk about the voltage difference. What they mean is an electric potential difference. Okay. But I'm going to do my best to say electric potential difference.
We have done stuff where it's been like newtons or something, or joules, and we've talked about it as newtons per kilogram or whatever.
Yeah, and that happens.
So I just wanted to know. So no, we are using volts.
The formal is electric potential, and I will do my best to not mess that up. Okay? All right. Because it's confusing. I know it's like we're learning a new language, and so hearing people use slang isn't really always useful, right? So I'll do my best to clean up my language. All right. So I'm just going to flip over the page. And so just to make sure we have it all on one page, for a point charge, and I've already told you what a point charge is. It's when all the charge is concentrated down to one point. We will say that electric potential, V, is equal to the electric potential energy divided by the charge that finds itself near the source charge or the point charge. I'm going to put this into a sentence format in just a minute for people that are sentence format thinkers. But if we rearrange this, we'll get electric potential energy equals V times the test charge. And normally people don't write that Q test. Typically what you'll see is electric potential energy, so that's E subscript E, equals VQ. So I'm going to leave it in this form because that's the pretty form that people usually expect to see this equation in. And I'll put it into sentence form just to make sure that this is clear. So if a charge, this is maybe one of those few situations where putting it in sentence form really does like make it more clear because it's something that is a little abstract, right? So if a charge is at a position where there is an electric potential due to other charges that test charge will possess electric potential energy. And that sounds like an awful lot of writing to explain what E equals VQ means. But I think that for some of us, it's nice to see it in writing. Nod of the head. How many people find it nice to see it in writing? Yeah? Okay. So a number of people. And it's weird how some things are best left in math and some things are best left in words for us to understand it. So I want to go back to this idea of work. And you can tell that I'm playing a little bit of table tennis. I'm going back and forth on this one, right? I want to go back to this other idea of energy. So we had this idea that work was equal to change in electric potential energy. And we sort of made that expanded out. We said electric potential energy at, I'm going to switch. I won't use A's and B's this time. I'll just say electric potential energy at position 2 minus electric potential energy at position 1. And using this new equation that we just came up with for electric potential energy involving electric potential and charge, we could say that could be turned into V2 times the test charge minus V1 times the test charge. And I want to draw a picture that sort of is like a cartoon explanation for this. So here we've got a positive charge. So this would be the charge that's, let's just say, causing the electric potential, okay? Call this the dominant charge in this situation. And, in our analogy to gravity, we talk about like Earth maybe being like the dominant mass and a satellite being like a test mass, like that's in the presence of, the gravitational potential energy of the Earth or whatever, right? So here I'm going to say that at some distance away from that charge, that point charge, I'm going to put a little electron. And anywhere that point charge is around that contour, because I mentioned contours earlier, it's going to have the exact same electric potential, no matter where it is. And what I'd like to suggest is that I could take it from that initial distance away from the charge, the central charge, and I can move that test charge out to another distance, let's just say out here, and we call that R2, and R2 would describe the equipotential surface contour that it would find itself at the new location. So I'm going to take myself from one location to another location, and I would have an associated R value, R1 and R2, and those R1 and R2 values would go into calculating my electric potential. Remember, electric potential could be written as K, maybe I really should call this Q test. K times Q point times Q test over R2, see that's the first V2 point value, times Q test, minus K times Q point, over R1 times Q test. And that would be the difference in electric potentials times the test charge, giving us the difference in electric potential energy. In other words, that's how much work it would take for us to move that negative charge to the next contour. And again, I want to try and like fall back on this idea of how this could relate to our understanding of gravitational potential energy. So this is electric potential energy. We're using electric potentials and test charges to figure out what the change in electric potential energy is. And I want to, again, lean back on our earlier grade school days of how we learned about contours in the past, because I'm calling these equipotential contours or equipotential surfaces for electrostatics. But if I just came up to you and said, oh, by the way, this is a picture of a mountain, you'd look at that and you'd think about your previous history in school and you say, oh yeah, I believe in that. That is a picture of a mountain. And if I said, hey, after today, this is a picture of a positive charge and an electric charge in its presence, you'd say, okay, I can believe in that. But I want to go back over to the mountain for a second, okay? If I was on the mountain and I had a person that was standing at that little spot there's a person, and I had a person that was down here, let's say it's the same person but at a later time, we would all agree that that person changed gravitational potential energies from one spot to the other. True? Here we've changed electric potential from one spot to another, and electric potential energy. Back over here, I could also probably convince you that if the person had ended up on this side, they started off near the top of the mountain, but then they moved to the bottom of the mountain, but maybe on the other side of the mountain, can you see that they would have lost just as much gravitational potential energy? Because the way contour maps work, they're based on the height, right? And we never talked about them as equipotential maps in geography class. We just talk about them as common height maps because we know that EG has some sort of relationship with mass times acceleration due to gravity times height. We know that the mass of the person didn't change, the acceleration due to the gravity didn't change, it's the height that changed. So I believe that the change in gravitational potential energy from position 1 to position 2, or position 2, we could even call it position 2A versus position 2B, because it's kind of like a choice, choose A and B. The gravitational potential energy would be the same difference either way. And the same thing would be true for our electric potential contours for electricity. Whether that electric charge ends up over here on the contour or like over here on the contour makes no sweet bit of difference, right? It's still the same change in electric potential energy. So that's my argument. And I think it stands on the shoulders of grade 9 geography, but hands in the air if that's a sold argument. Are you buying what I'm selling? All right, cool. And I kind of am really trying to lean back on our previous knowledge because I feel like this is outside of the scope of our everyday, right? So we got to try and lean on the everyday as much as we can anyway. So I want to do an example problem, and I'm going to try and keep my writing on the small side because otherwise I'm going to run out of space. I've left myself with more than half a page, and I don't know where you are with this. So I'm hoping you don't have to grab a new piece of paper. But here's the question. Find the electric potential at P for the following. So here's the situation. I've got a positive charge, and here's point P, and point P is a certain distance away from my positive charge. I'll just give the values. We'll say that it's at position RA equals 0.40 meters. Just put it right there. It's cool. Oh, right on the stool is good. Thank you. And we already know from the past K is equal to 8.99 times 10 to the power of 9 Newton meters squared per Coulomb squared. And let's just make up a new value that the positive charge has a value of Q equals positive 6.4 times 10 to the power of negative 6 coulombs. So if the question is, find the electric potential energy at that position, let's do that. Let's call this question A. And so for question A, I think it's fairly straightforward, but I'll set it up and I'll ask you folks to do the calculations. V is equal to K times Q. And remember, it's the point charge Q. I don't have any test charges yet. I haven't put any test charges into the situation. It's the point charge Q divided by R. So sub in your values, actually calculate it. And at this point, I think part of the challenge is just making sure that you're going to be able to do the scientific notation. So please do the data entry into your calculator. Make sure you can do this, okay? We'll share our answers. Not worried about that. You beat me to it, all right? How'd you get it done so fast? I don't even know how to have it written yet.
I have a button that lets me save stuff into my computer, so I can just save at the beginning of every lesson. I put in the K value.
All right, well, you're just a calculator ninja. All right, what'd you get, calculator ninja?
143840.
Yeah, that sounds right. So I had jotted down 1.43840. I'm glad that we agree. Times 10 to the power of 5. And then the units would be, you could write them as joules per coulomb, but like nobody does. They write it as volts. So I'm going to throw it as joules per coulomb first, and then I'm going to write it as 1.4, for sig figs purposes, 1.4 times 10 to the power of 5 volts. And it does seem so weird. Like, I mean, heaven forbid that you have the same unit and variable. Doesn't it look weird though? Like I've done something wrong? Like V and V? Oh my gosh. That never happens. So electric potential is just V though, so that's nice. All right, so yeah, we could do a little therefore statement, but 1.4 times 10 to the power of 5 volts. I want to try and make this like a little bit trickier. I'd like to add a little bit to this. If a test charge RB equals negative 1.0 microcoulombs is moved from P to a position 0.65 meters away from the test charge, or from the point charge, how much work was done? Okay, and as I write that out, I mean, I don't even have to slide my page around. Can you see that the format for the solution is right up here? The change in energy is going to be really calculated using this method, right? Now, if you wanted to get fancy with this equation, I'm going to get fancy down here. I'm going to expand it out a little bit, and I'm going to say delta EE is equal to, I could factor the K, Q1, Q2 out of this expression, and I could write it as delta EE is equal to K times Q point times Q test, because Q point and Q test and K are all present in the numerator of both of those values up here in the previous setup, times 1 over RB minus 1 over RA. Now, I'm being really careful here. I am not putting absolute values around the Q's. Do not put absolute values around the Q's. We did do a little bit of absolute valuing of the Q's for when we were doing forces and electric fields, because we were going to use the field orientations to figure out the positives and negatives for the reference frame. But with energy, it's a scalar. So we need those positives and negatives, because you could have negative potential energy and positive potential energy, and that's okay with positive and negative charges. So I'm going to ask you to be thoughtful in this, in regard to this. Do not absolute value the Q's, and I intentionally chose a negative charge for this one on, make sure that everybody was sort of following that rule, okay? So as you sub in your values, I'm going to write in all my values, but as you get to the solution, put your hand up once you've got it. We'll share our answers. We'll do a little bit of physics democracy, and hopefully we all vote for the right winner, okay?
Is there a part C?
Oh, no, this is part B.
No, is there a part C?
Oh, there is no part C.
Okay.
Because I don't think you could fit it onto the
Yeah,
page.
that's why I was asking.
Yeah, no, this is part B, and that's all she wrote. Yeah. Newton meters squared per coulomb squared. I mean, we could do a part C if you really want to. Yeah, me too. And remember, when you're going from microcoulombs to coulombs, 10 to the power of negative 6. You feel like you're going to run out of space, but then at the very end, it's just like 1 over 0. What was our B again? 6.5? Minus 1 over 0.40.
If it's that far away from the point charge, wouldn't it be that plus? Oh, never mind.
Good. Yeah, we're just doing final minus initial.
Is that a -6?
Yep, negative 6. Remember, a microcoulomb is a millionth of a coulomb. 10 to the negative 6.
I have an answer, but I have no confidence in it also.
All right.
I will say it's second.
You'll say it's second. Who wants to be first? Yes, sir.
0.055.
Does anybody want to second that motion?
I agree.
All right, the motion seconds. Anybody want a third? All third. Motion carries. All right. 0.055 joules, or we could write it as 5.5 times 10 to the power of negative 2 joules. Amalgamated 2 and joules to one word. So yeah, 5.5 times 10 to the power of negative 2 joules is how much energy it would take to move that little charge away from this other charge. And I keep on calling it an electron, I think, but it's not an electron. It's just a random charge. I didn't give it the exact charge of an electron, so I can't say that. I could have been more specific and detail-oriented, I guess. So just some random negative charge moving away from a random positive charge. And we did a little bit of work to do it. And really, like, this idea of calculating changes in electric potential energy really is very much like these ideas that we saw once upon a time where we took, rocket ships and flew them away from the Earth, right? And in those days, we were doing gravitational potential energy. And I remember in those days, I was saying, there's going to be some analogy later on that I can draw back to talk about this, to make sense of it. And it's good. We're seeing the same patterns come up over and over and over again. It's nice. That's encouraging in the math to see that the world really does follow patterns. It's lovely. And it helps us to sort of analyze things that are new and different. I think that's all the big things that I wanted to talk about. Oh, you know what? I want to say anything about that? I don't know. Just a reminder that since you could be talking about a negative charge, as we are right now, going from one position to another position, and we're talking about that change in electric potential energy being a positive answer, do you figure that you could probably do something similar where you take a negative charge and you move it closer and it would be a negative answer?
Yeah.
And so it's okay to have negative changes in electric potential energy. So I just want to throw that out there so there's not like some feeling of shaken confidence if you get negative answers and you feel like you haven't seen that before. It's okay. All right, I think that's all I'm going to say about that. I'll stop recording.